This is Unit 2, and we're in Section H. We've been working with the chain rule for derivatives, and we're now going to have the opportunity to revisit some of our applications of derivatives. And in these cases, these applications will also utilize the chain rule. Our first problem says find the equation of the tangent line to the graph y is equal to x squared minus 3x to the 5th power at the point where x equals 1. Remember, to find the equation of any line, we need a slope and a point. So the slope here, because it's a tangent line, is going to be our derivative. And the derivative of this function would be 5 times x squared minus 3x to the 4th power. There's our power rule. And then we multiply by the derivative of the inner function, 2x minus 3. And if I now plug in my x equals 1, like so, what have we got? Let's see, that'd be 5 times negative 2 to the 4th times negative 1. And I'm coming up with negative 80 as my slope there. Our point, they already gave us x equals 1. So plugging that in to find the y value, let's see, that would be negative 2 to the 5th or negative 32. And so y equals mx plus b. We'd have negative 32 equals negative 80 times 1 plus b. And adding that 80 over there, we'd get 48 for b. So the equation of my tangent line is going to be y equals negative 80x plus 48. All right, let's stick with that application of derivative as slope in problem 2. Here we've got a function given, and the first thing we'd like to know is where is the tangent line horizontal and where is the tangent line vertical. In both cases, we're going to need the derivative because horizontal would be the slope or derivative would be 0, and vertical lines, the slope or derivative would be undefined. So either way, we need to know what the derivative is. I'm definitely seeing a product rule. So let's write that out first. F would be x. And g is going to be that cubed root, which I'll write as 4x plus 3 to the 1/3. F prime will just be 1. And when I go to do g prime, I'm going to watch for this chain rule. We have our 1/3 times 4x plus 3 to the negative 2/3, power rule, and then multiply by the derivative of the inner function, which would be 4. And then I'm going with a product rule here, so fg prime plus gf prime. All right, fg prime, I would have 4/3 x times 4x plus 3 to the negative 2/3 plus gf prime, just 4x plus 3 to the 1/3. All right, so for part A, the horizontal tangent line, I'd like to know where the slope or derivative is equal to 0. And this is something we actually looked at before. This negative 2/3 power is actually a 2/3 power in the denominator. So if I were to rewrite this and put this as 3 times 4x plus 3 to the 2/3, kind of helps me see what I want to do when I clear my fractions in the next step. So if I want to clear my fractions out of this equation, I'm going to multiply both sides by this denominator. And that means it's just going to cancel out the denominator here, leaving me with 4x. And here I'm going to get a 3, and then this will be 4x plus 3 to the first power. 2/3 plus 1/3 is first power. And of course anything times 0 is 0. And so I've got 4x plus 12x plus 9 equals 0. 16x is negative 9. And x would be negative 9/16. We wanted the points, so to get the y value, I'll just plug that x back into the original function. And I'm probably going to end up getting a decimal, we'll see. Yeah, nothing too nice there. I ended up with about negative 0.487. So as long as I'm going decimal, let's do the 9/16 to the negative 9/16 as well. Actually, that's equal to 0.5625. So the point at which the graph has a horizontal tangent is 0.5625, negative 0.487. All right, in part B, we wanted to know where that tangent line is vertical. So for vertical, we want our slope or our derivative to be undefined. And typically things are undefined when the denominator is 0. So if I kind of use that same idea again and just rewrite this first term, putting that 4x plus 3 to the 2/3 power on the bottom, oops, 1/3. If this is 0, then that puts a 0 in the denominator, and f prime will be overall undefined. So that actually gives me an x is negative 3/4. That's causing that undefined derivative, or a vertical tangent line. And again, I could just plug that in to the original function to find the y value. Let's see, that's actually going to be negative 3 plus 3 under that radical, so y is going to be 0 here. So at negative 3/4 or negative 0.750, we're going to have a vertical tangent line. All right, let's take just a moment and take a look at a graph on that one. And before we actually go to the graph, as I was prepping that, I just realized I hit a wrong button when I put this into my calculator. Check that value again, but I actually should have gotten negative 0.511 rather than negative 0.487. So let me just fix that. There we go. So that's where we're expecting to see a horizontal tangent, and right there we're expecting a vertical tangent. So if we do go over to our Desmos screen here, I went ahead and typed in the function, so you can see it right there. There's the graph of our function. And our horizontal tangent line would be down right around here, where you see that minimum. And there it is, negative 0.5625, or negative 0.563 if we round, and negative 0.511. All right, what about the vertical tangent? Can you see it right here? Right here, the graph goes just instantaneously vertical, and that is at that point negative 0.75, comma 0. So what we predicted is exactly what we got. Okay, let's try something other than a slope application. This next one, I think, is just a general rate of change application. In number 3, a cup of hot coffee is placed on a table. The temperature T of the coffee after little t minutes follows Newton's law of cooling, and the temperature is given by 130 e to the negative 0.08 times little t plus 70. So first of all, we would like to know what is the initial temperature of the coffee and how fast is it cooling initially. So the temperature is going to be T, but how fast it's cooling, that's the rate of change of T. So that's going to be T prime. So we're being asked a question here about both T and T prime, initially or at little t equals 0. So here's my capital T. Let's go ahead and do the rate of change, or the derivative. We'd have 130 times. The derivative of the exponential is itself. And then the chain rule would give me a times negative 0.08. Plus the derivative of 70 is 0. And let's see, 130 times negative 0.08 is negative 10.4 e to the negative 0.08t. So initially, that is at time little t equals 0. I'm just going to plug in t equals 0 into both of these equations. The temperature at time 0 would be 130 e to the 0 plus 70. Of course, e to the 0 is 1, so that's 200. And t prime of 0 would be negative 10.4 e to the 0, which is negative 10.4. So initially, the coffee is 200 degrees and is cooling at the rate of 10.4 degrees per, was this in minutes? Yes. So we've got our initial temperature and also our rate of change. By the way, because I said cooling, I didn't include the negative in my description. The negative is that cooling or reducing in temperature. It's already part of the description, so I don't want to use the negative sign on the 10.4 when I say that. All right, what about part B? Find the temperature of the coffee after 15 minutes. And again, how fast is it cooling? Well, we've got all of the hard work done. We already know the function and its derivative. So if I just plug in t equals 15, let's see, that's going to give me the temperature. And it looks like 109 degrees if I round off to the nearest degree. As far as the rate of change of the temperature, or how fast we're cooling at that time, if I plug 15 into the derivative, I am going to get negative 3.1 degrees per minute. So after 15 minutes, the coffee is 109 degrees. And it's cooling at a rate of 3.1 degrees per minute. All right, one more part to this. In C, we're supposed to find and interpret the two limits. Capital T goes to 0 and capital T prime goes to 0. Excuse me, goes to infinity, not 0. Can't read my, apparently that was too small a print for me. We want the limit as little t goes to infinity of capital T. And capital T was 130 e to the negative 0.08 t plus 70. This is going to become e to the negative infinity. And that goes to 0. So I'd have 130 times 0 plus 70, or 70. So after a really long time, the temperature of the coffee will be about 70 degrees. In other words, it's basically going to decrease in temperature till it hits about room temperature, and then it's going to stay there. Let's do the limit of the derivative, and then we'll write it all as one sentence. So the limit as t goes to infinity of t prime would be the limit as t goes to infinity of negative 10.4 e to the negative 0.08 t. And once again, this part right here, when I put infinity in, that's like e to the negative infinity. So that goes to 0 again. I have negative 10.4 times 0, or 0. So the temperature is no longer changing. The rate of change of temperature is now 0, which makes sense if the coffee's kind of leveled off in temperature at 70 degrees. So we would say after a long time, the temperature of the coffee nears 70 degrees and is no longer changing. That is, the rate of change is 0. All right, we have one more application problem to take a look at here. In number 4, a weight is attached to a spring, and the position of the weight at rest is defined as S equals 0. The system is set in motion by pulling the weight down and releasing it. In the absence of damping, meaning we're not including anything like air resistance, the equation describing the position in feet of the spring, actually that should really be of the weight, at time t seconds is given by S equals -3 cosine pi x over 4. Oh my goodness, I got a couple mistakes here. That should be pi t, right? This is a t as my variable. Let's fix that. There we go. All right. I would like you go ahead and fill in the information in the chart. Notice for a bunch of different times, we're asked to find a position, a velocity, and an acceleration. Now we were given the position equation, so that one's no problem at all. The position is just going to be s, and all I have to do is plug in these various values for t. Right? The velocity, though, is going to be the derivative, s prime, and the acceleration will be the second derivative, s double prime. So let's go ahead and find those derivatives, and then maybe we'll cleverly use some good information in our table to fill this chart in really quickly. So s prime, I would have the derivative of cosine, which is negative sine. So negative times negative will make that a positive 3, times the sine of pi t over 4, times the chain rule, so the derivative of the inside function would be pi over 4, right? That's really pi fourths times t. So the derivative is pi fourths. Or I could write that as 3 pi fourths sine pi t over 4. All right, our acceleration would be our second derivative. The derivative of this, first of all, I've got my constant multiplier, 3 pi fourths. Derivative of sine would be cosine, pi t over 4. Again, remember the argument of the trig function stays the same. And then here's that chain rule again. The derivative of pi t over 4 would be pi over 4. So I end up with 3 pi squared over 16 times the cosine of pi t over 4. All right, just to make it really easy to plug in values, let's put all three of our equations into the calculator. I want to go ahead and put in my equation for s. So y1 is going to be the s equation. And by the way, let's just make sure here, I should have checked this first. I am in radian mode, so that's good. All right, my s equation is -3 cosine pi, and I'll have to use x over 4. y2 is going to be my derivative. That is 3 pi over 4 times the sine of pi x over 4. And then finally, the second derivative is going to be 3 pi squared over 16 times the cosine of pi x over 4. All right, so I've got them all in there. If I now go to my table, I can plug in whatever I want. And the first thing I want to plug in is the time of 1 second, so that would be an x of 1. And then notice I should just be able to go right across. My first one was s, so -2.121. The second one is velocity, 1.666. And if I go over one more, the third one is acceleration, 1.3085. If I go on down, and the next time I want to put in is 3, and again, just going right across, Position is 2.121. Velocity is again 1.666. And negative 1.309 for the acceleration. We want to put in 4. Position is 3. Velocity is 0. And acceleration is negative 1.851. And finally, times 6. That's negative 3 with an exponent of negative 13. So negative 3 times 10 to the negative 13th. That's basically just 0. Velocity of negative 2.356. And an acceleration again of basically 0. It says describe the system at each of the times listed. I won't write out all of these, but let's maybe just pick 1 or 2 of them to discuss. If I start with at time 1 second, what I can see here is that my weight is about 2 feet below equilibrium. So 2.121 feet below equilibrium. As this weight is bouncing up and down in the spring, it's got a positive velocity, so it's moving upward. At 1.666 feet per second. And it's accelerating at about 1.3 feet per second squared. So, you could actually do this kind of thing for any of these points. Maybe I won't write the other ones out. You can get the idea. But essentially, you can tell the story of what's going on with the weight at any time that you'd care to do so. All right, that brings us to the end of this section.